this problem solving session, we solve one problem divided into two parts that will make heavy and critical damping clear to you. So, the problem is like this. We have a weighing scale or a large weighing platform, which you may have seen near the railway stations or near where the sugar canes and things like those trolleys are weighed. So, this is basically has a lot of springs underneath it, and whatever you want to weigh comes on top of it, and this fellow goes down. So, what we have is weighing scale, and by scale I mean it's a large scale, is made by attaching a horizontal platform of 50 kilograms to a spring system So, this is a spring system here. Now, I am marking it red. So, these are many spring systems that have an effective K of K equals 5000 newtons meter inverse. In addition to the springs, the platform attached, it is also attached to a device. It could be, for example, some rods here which are put in some liquid or in some thing that damps the motion. So, attached to a device that damps its motion and makes it critically damped for 500 kgs on the platform. So, if I put 500 kgs on the platform, then this is critically damped. Now, what we want to do is, I will make two parts of this problem. First part is, if a 500 kg load is dropped on the platform from a height of 1 meter, find the subsequent motion of the platform. And part 2, instead of 500, if a 200 kg load is dropped on the platform from a height of 1 meter, find the subsequent motion of the platform. I should write platform plus the load. In the top problem also platform plus the load, because the load remains on the platform. So, let us see, just to analyze the problem, what do we have the initial problem as? Mx double dot plus Bx dot plus Kx is equal to 0. So, we have x double dot plus gamma x dot plus omega 0 square x is equal to 0 when we solve this problem. And in this case, when I take x equals some e raised to lambda t, I get lambda square plus lambda gamma plus omega 0 square is equal to 0, or lambda comes out to be minus gamma plus or minus square root of gamma square minus 4 omega 0 square whole thing divided by 2, which comes out to be minus gamma by 2 plus or minus square root of gamma square by 4 minus omega 0 square. Now, so gamma, you see, B is given for the system and gamma depends on the mass. So, for critical damping, I have gamma square over 4 is equal to omega 0 square, and gamma is B square, gamma is B by m. So, 4 m square is equal to omega 0 square. For heavy damping, I have gamma square by 4 greater than omega 0 square, and therefore, B square over 4 m square over is greater than omega 0 square. Now, what we are given is that this platform is critically damped when I put 500 kilograms on this. If I decrease the mass, you see this value, gamma value will go up, and therefore, the system will become heavily damped. So, in these cases, either the motion, in the first case when a 500 kilogram is dropped on the platform, the motion is going to be critically damped, and in the second case most likely is going to be heavily damped. I am saying most likely because omega will also change, and that we will check. So, first case, this platform is anyway critically damped and we are dropping this 500 kg weight load on this. What are we given? We are given K equals 5000 newtons meter inverse. The mass after the weight drops is going to be 550 kg, and therefore, omega 0 square will be equal to K over m, which is 5000 over 550, which is going to be 500 by 55 or 100 by 11, roughly 9. So, omega 0 is 3 radians per second. What about gamma? Gamma is equal to 4 omega 0 square root or 2 omega 0, which is going to be 6 radians per second. So, B over m is equal to gamma implies B for the system is going to be 6 times 550 kgs, which is 3300 kg radians per second. This B is given for the system, it is fixed, just like K of the spring is fixed, B is also fixed. It's the mass that changes the omega or the gamma. Now, what is happening is, as this mass falls on the platform is going to have initial speed. Now, by momentum conservation, I am going to have mv is equal to constant. So, I have 500 kgs falling from a height of 1 meter. So, 2 gh gives me 20 is equal to, now the mass is going to become 550 v. So, v becomes 10 over 11 square root of 20 meters per second. So, let me look at this system again. Here is the platform and I am just showing 2 springs. When it is 50 kgs, it is at a certain height y. and when this load comes on top of it, the platform goes down, because now it has, if I just put this load here, it would have gone down. So, this will be the equilibrium position for 550 kg. So, this distance is where this entire mass equals 550 kg system is initially. So, y at 0 is this distance, y at 0, which is going to be equal to 550 times 10 mg divided by k, 5000, minus 50 times 10 over 5000. So, this comes out to be 50 times 10 over 5000 out, 11 minus 1. 50 times 10 over 5000, which is 1 meter. So, now the problem is very clear that y at 0 is equal to 1 meter, y dot at 0, the platform is coming down. So, y dot at 0 is minus 10 over 11 square root of 2 meters per second, and since the system is critically damped, displacement yt is given as a e raised to minus lambda t plus bt e raised to minus lambda t. In critically damped, lambda is the same, and what is the value of lambda? Lambda is equal to nothing but minus gamma by 2, which in this case will come out to be minus 3. So, I have yt is equal to a e raised to minus 3t plus b t e raised to minus 3t. And I also have these two initial conditions, and therefore, I can solve for the motion. So, y0 is equal to 1, which is going to be equal to a, that is it, a. So, this gives me a is equal to 1, and y dot at 0 is going to be minus 3a plus b, and the third term is going to be 0, and this is equal to minus 10 over 11 root 20, which comes out to be minus about minus 4. So, we get a equals 1 and minus 3a plus b is equal to minus 4, which implies minus 3 plus b is equal to minus 4, or b equals 1, and therefore, the motion yt is going to be given as b comes out to be minus 1 e raised to minus 3t minus t e raised to minus 3t, which is 1 minus t e raised to minus 3t. In part 2, what we are looking at is if the load being dropped is 200 kgs instead of 500 kgs, what is going to be the subsequent motion? So, again, let me make this system, and I have put a load of 200 kgs here. So, first let us calculate what the initial velocity is going to be. This time I am going to have 200 square root of 20. This fellow falls down. By momentum conservation is going to be 250 times v. So, v going down is going to be 4/5 square root of 20 meters second inverse. And what about, so this is v at 0, and this is going to be, so y dot at 0 is going to be minus 0.8 square root of 20 meters second inverse. What about y0? y0 this time is going to be 250 times 10 divided by 5000 minus initial mass is 50 times 10 over 5000, which comes out to be 200 times 10 over 5000, which is 0.4 meters. So, what we have is y0 is equal to 0.4 meters and y dot 0 is equal to minus 0.8 square root of 20 meters per second. What about the motion? Now, this time, as we have already decided, motion could be heavily damped. So, let us check that. I am putting a question mark. We have already determined that B is 3300 kg radians per second and K is 5000 newtons per meter. So, gamma this time is going to be 3300 over m, which is now 250 kgs, and this comes out to be 13.2 radians per second, and omega 0 square comes out to be k over m, which is 5000 over 250, which is 20. So, now gamma square over 4 is going to be 13.2 square over 4, roughly 170 over 4, which is about 40, and omega, which is greater than omega 0 square. So, the system is indeed heavily damped, and therefore, the motion is going to be given by y t equals a e raised to minus lambda 1 t plus b e raised to minus lambda 2 t, where lambda 1 is nothing but minus gamma by 2 plus square root of gamma square by 4 minus omega 0 square, and lambda 2 is equal to minus gamma by 2 minus square root of gamma square by 4 minus omega 0 square. And we have already calculated the values of gamma and omega 0, and they in this case come out to be minus 1.75, or I will just put it plus because we have taken the minus sign already up there, and this comes out to be 11.45. And therefore, your motion is y t is equal to a e raised to minus 1.75 t plus b e raised to minus 11.45 t. Now, y at 0 is given to be 0.4 meters, and therefore, I have a plus b equals 0.4, and y dot at 0 is minus 0.8 square root of 20 meters per second, and therefore, I have minus lambda 1 a minus lambda 2 b, which is equal to minus 1.75 a minus 11.45 b is equal to minus 0.8 root 20. So, I have two equations, 1 and 2, and I can solve for a and b. After you solve this, that I leave for you to do, what you get is y t is equal to 0.103 e raised to minus 1.75 t plus 0.297 e raised to minus 11.45 t, and that is the answer in the second case.